Good morning, all, and welcome to the another session of Structural Analysis 2. I hope you all are doing well and ready to carry on with the another session. I hope this time the voice is clear to you. Uh, I am able to communicate properly with you and you are receiving the voice correctly. So, in case, give your inputs in the chat box for a while. Please let me know whether am I audible properly or not. Okay. So it's clear. Yeah, thanks. Thank you. Thank you. So I hope you all are super excited to go with the another session. And today, as we discussed in the last session, it's your second session only. However, we'll start high and we'll be beginning with a analysis of fixed beams. In the last session, we started with the introduction on the course. We went through the entire range of the topic. Also, we went through the credit details and the faculties details, right? So, what I would like to advise, as usual, uh, that's what we did in the last semester also. Please have your scribble tools, like writing tools, with you next onwards, not this time. Don't worry, and try to note down important points. And whenever there is a case of the numerical, it would be better practice to keep writing as we progress in the lecture. Today, I have not scheduled any quiz. However, in the last quiz, I would definitely like to share my experience. Most of you did good in the test. There are 4 to 5 students at least. Those who have scored more than 10 out of 10. It was a 10 marks test and 2 marks of each nearly. However, I'll get back to the detailed analysis on those test results, because whenever we hold a quiz, we are dedicating time, we are putting an energy on, on such kind of efforts. There should be a closed cycle, like uh, it should not it should not go into the drain. So my point is, those who struggled with, uh, less than 5 out of 10, I have scheduled something for them. And those who are interested, they can be a part of that also. We shall be discussing the concepts, couple of concepts of the earlier semester that we have discussed in S7. Right. So some of the important methods and formula, as well as some equations and procedures. So whatever I delivered in the last semester, I think it's a good time to rebrush them quickly. So probably in the next week, I shall be scheduling it, of course, during our own schedules, so that you don't get disturbed in your regular schedules. So in the next class, I think we will have a review of some of the important concepts which we earlier have understood but could not recall properly, right? So it will help you overall, all the students, to rebrush the knowledge, as well as getting connected with the upcoming topics properly. That's what I think. It's a good practice, right? So let's go ahead in today's session. uh, this is what we did in the last class. Now you have 4 lectures and 6 units in your course, and you are expected to carry out analysis of indeterminate structures, right? So we will have a review of the session, last session. Indeterminate structures we went for, and we understood the needs and benefits and limitations also. The limitations as such are not serious limitations, but I would say you require some complex methods to understand, and high-end methods are there, which you can employ to analyze the indeterminate structure. So in a way, it is a limitation, but it's not actually the limitation. Right? It's about developing your skills to analyze this kind of structures. So we also went through the some of the uh, analysis methods, like we discussed about the energy principle methods, like moment area method, slope deflection method, matrix methods. We enlisted all these methods, and we also discussed how to apply the theory into the practice, why we require these high-end methods. We understood it by taking an example of a simply supported beam where we were comfortable to find out all the necessary quantities, namely the external reactions at the supports, uh, internal forces like shear force, bending moments, and overall deformation characteristics like displacements, and even you can find out the slopes of the determinate structures with typical equations and methods, simple methods. However, now we want to use these methods in a different perspective. So we also find the relationship between new and old concepts, and finally we went for a quiz. So today's session is dedicated on fixed beam analysis. We'll have an introduction. We'll have some real examples. I'll more than happy to show you how you can pursue, how you can visualize fixed beams in the structures around us. Right. So I have collected some photographs which will definitely demonstrate how the fixed beam look like, right, in real life. And second, basic behavior we'll understand, and special features of the fixed beam that we will also discuss. So let's go ahead. I have not done any change in this page. I hope you will be, exploring this once again, and then onwards, like after say second or third session, I will be changing this page. That means I'll be changing the content of this page particularly. So today keywords remains as it is, but one keyword we can definitely add over here, that is a fixed beam itself, right? And fixed moments are the moments which develop at the fixed supports of the fixed beam. So that you can also add over here as a keyword of today's session. So a beam member with both its end rigidly connected with the supporting members is referred as a fixed beam, as simple as that. So an element, a linear element, which is known as beam, when it is rigidly connected at both ends, equally rigidly connected at both ends, it is referred as a fixed beam. A fixed beam is a statically indeterminate structure by 3 degrees. Like when you try to obtain the statical indeterminacy of fixed beam, typical fixed beam, you have three reactions at one end and three at the other. So total goes like six, and we have available conditions of equilibrium as three. So when you take a balance of this unknowns and required quantities as unknown, and available equations of equilibrium as 3, so 6 minus 3 gives you 3 answer, right? So typically a fixed beam is indeterminate by 3 degrees statically. However, the kinematic indeterminacy is 0. That means what? See, the beam is not free to move in any of the direction, neither at the support or throughout the span practically. However, there is always a deflection which is possible at the ends as well as in the span. So we'll keep this factor aside. And as far as the joint displacements are concerned, because kinematic indeterminacy deals with the joint displacements, as you know, right, from the past learned concepts. So in a fixed beam at a joint, none of the displacements are possible, like a vertical, horizontal, as well as rotation. That is why it is called a rigid connection, and that is how the fixed support develops itself. So here you can see there is a typical look of a fixed beam. And this is an international, you can say it's a standard symbol of a fixed beam when you have both hands fixed, and this is a standard symbol of a rigid support or a fixed support. So at both ends you have rigid connection. That beam is known as fixed beam, as simple as that. Now let's go to the field, right? Here I have collected couple of images which resembles the fixed beams in real structures. Like here you can see there is an RCC wall, and within RCC wall you have metal plate that is bolted within the wall itself, so that the rigid connection is developed between wall and plate. And further to the extension, the fixed beam that you can see here, fixed beam is connected with those plates. If you go into the last segment over here where the cursor is moving right now, you can see here that already there is a plate which is mounted rigidly connected on this wall. However, beam is yet to get connected. But you can see this angle which is pre-installed, prefixed on this plate. And when you insert your beam, and finally when you use the bolts or the welding process, you can create your fixed beam connection. Right? So this is the glimpse of, or we can say this is an example of fixed beam in real life. Right? So now how can you identify fixity, or how can you say that this joint is a fixed joint? So in real life I'm asking, right? So let me give you some tips. First thing, just look into the type of connection of actual beam that is supported or connected with the other beam or other elements, and see that is there any fixtures or is there any monolithic casting that has been practiced or not. If your answer is yes, then you can say that you don't have any possibility of any sort of kinematic movement of the beam. Here you can see, for example, here is a plate, and plate is rigidly connected with the wall. So plate cannot move in horizontal or vertical direction at all. So it is itself is a rigid structure, first of all. Then on that addition, you can have an angle, and that angle is further rigidly connected with the wall as well as with the beam, in a way that this connected plate restricts the movements at the joints for rotation, translation in vertical and horizontal direction. So that is why we can identify this joint as a fixed joint or fixed support, whatever you call, right? When it is ending at a point, it is support. When it is connected further, it is called joint. So it may be a fixed joint also, or it may be a fixed support also. Support means the arrangement which is ending at a point and which is transferring basically the total force coming from the beam to the support itself. Right. Normally we have a wall, we have a column, we have similar arrangements where you can rest your beam on those members. So they become support. But many times you require extension of the beams. And to extend a beam, definitely the most important joint is the rigid joint. That means it is the fixed joint always, right? Because fixed joint allows the extension of the span of the beam. If you don't use fixed beam, fixed connection in extension of beams, it will end up working as a beam. It will not remain as a beam anymore, because the primary duty of a beam is to undergo bending. I'm giving you a logic. So when you load the beam, beam has to bend. Now to bend, the beam should be continuous, right? So the moment you connect one beam with the another beam with non-fixed type of joints, at that junction the transfer of moment will not be possible anymore. So we cannot classify or qualify that element or arrangement or extension as a beam itself. So always remember, whenever you want to extend your length of the beam by connecting two pieces together, always go for 100% rigid joint in any case, any material. Let it be a steel, let it be a timber, and let it be an RCC itself. So I have collected more references, more images for all these three materials. Right now you can see that this is a composite connection. It is not 100% steel, it is not 100% concrete. So this kind of connection is known as composite connection. Right. So you can develop fixed support or fixed joint in any sort of arrangement, whether it is a same material or whether it is different material. Now this is 100% steel structure, right? So you can see that there are two columns, main columns, which are supporting the beams, right? So you can see here where the cursor is moving. This is, for example, a beam, right? And this beam is rigidly connected with this column. Similarly, this arrangement repeats itself, right? You can see everywhere, anywhere, right? In this case. So here you can see there is a small cantilevered beam which is projected from this beam itself, but you can see, if it is possible for you, you can see that there is a welding which is done. So welding gives you 100% rigid connection. So this is again a fixed joint or fixed connection for this cantilever. And as you know, the cantilever characteristic of a cantilever, one support is always a rigid or fixed support. And that is why it is satisfying over here that need. Right? However, our focus is here you can see that the steel sections are connected with this column rigidly by means of tight bolting as well as welding. So both ends for this particular beam is fixed. So we can say that it is a fixed beam. Now, when the entire structure is having fixed beams only, it is called moment resisting frame, because you know that the moments are developed only at the fixed ends. Not it is possible to get developed at the simply supported beam. We know that at the end of the simply supported beam, we don't have any active reaction to the moment. We have only maximum two reactions. One is vertical and second is horizontal if the support is a hinge support. Right? But if you employ the fixed support over there, you have an additional reaction in terms of reacting moments. That means what? That means your beam as well as your entire structure or even the entire frame is capable to resist and react against moments. And that is why it is called moment resisting frame or moment resisting structure. So if all the beams are rigidly connected with all the columns, that entire structure, entire setup or frame is known as moment resisting frame. But please keep it in mind that not all the frames are qualifying as 100% moment resisting frames. That is a separate point, and don't worry about it, don't think about it much. I just wanted to give you a glimpse because moment resisting frame is not a point of our interest right now. I just wanted to give you a reference. So here you can see this beam qualifies, this beam qualifies to be called as fixed beam. And if I apply a force here, then it will directly get transferred to both ends effectively. Right. So I just selected this image just to show you that how the same material can develop the fixity. So here the column is made out of steel I section, you can see here. Also this is an I section, and both are connected with each other by means of rigid connection. Now if you avoid welding over here, for example, you can turn this connection into the pin connection or partially rigid connection. Right. So that is also called as non-moment resisting frame, where the moments are only transferred within the beam itself, but not transferred on the column. Sometimes it is beneficiary, sometimes it is intentionally done. But when it is done, when not to do, that we will discuss later, because today's aim is just to have an introduction to the fixed beam, that's all. So let's keep it simple, and this is the image which explains the fixed beam. I have collected another images, where some images which shows the timber beams, or ideally we can say timber planks, right? So these are called timber joists. The main beam, which is called girder, and the secondary beam in the timber structure is called joist. So joists are thin members, and usually supporting the floors and finally transferring the floor load to the girders. And girders are nothing but the same, made out of timber only, but having large dimensions, and they can span more than the joists. So here I just have selected this image just to show you that it is definitely possible for us to develop rigid connection in any sort of material. So this is another material, right? First we went through the composite material where concrete and steel were connected. Then we went for steel alone, and now we can see that timber alone. You can go one more step ahead and having the column of the timber also. That is why I have selected this next figure. You can see here this both figures having a column made out of timber itself. Now you may have a question that how this joint may have get developed. So there is always a concept of the grooving. You can create a groove, right? You can carve the particular portion of the timber structures, and you can insert, encase this beam with some protruded part inside this particular beam. So they are nearly fixed in each other. So we can say that it is a encased beam. There is another name or synonym of the fixed beam is called encased beam. Let me give you an example. Like you may have seen the lintels on the or the chajas on the windows, right? So lintels are actually inserted inside the brick wall. Some portion, let us say not more than 4 to 5 inch portion of the lintels are inserted, encased inside the wall itself, right? So when you do that, actually you are offering fixed joint to the lintel, because lintels are responsible for long protrusion or long extension of the concrete chaja, right? So there is a plate like structure of the concrete RCC, and which protects your window also, and bears the forces sometimes, right? And they are utilized as the elevational decorative part also many a times. So in that case, you are offering indirectly the fixed joint. So here I just wanted to show you that it is definitely possible for us to create fixed joint in any member practically, any material practically. So here there are bolts which are used. You can see there is a channel like platform within which you can sit your fix your particular joist, and then when you offer bolts, always remember you should use minimum 2 bolts to ensure the fixity. If you use 1 bolt only, it will be end up with the pin connection, because it cannot offer the reaction to the moments. But here you can see that there are more than 1 bolts used, and that is how we can expect some sort of fixity within this beam itself. And it is not at all necessary that the beam should be continuous. They can end up over here also, and you have to take care about that fixed joint also. Here you can see another image where the different depth of the two beams are connected with a common column. However, the way of connecting is same. Here you can see there is an angle. So the angle is first welded with the column, and then the another outstanding angle leg is connected with the web of this I section by means of series of bolts. Here you can see them. So this all bolts ensures the fixity of this connection. Right? So you can expect that there is no horizontal displacement which is possible for any of these two beams. or neither the vertical displacement is possible, and this connection is capable to offer equal and opposite moment also. So that is how it gets qualified to be called as fixed beam at the end. Now one more detail I would like to discuss, that you can spot here. This is the junction where you can still use upper and lower angles to achieve your 100% fixity. Here you can expect up to 75% of the fixity. This is the biggest challenge in the design of the steel structures. You will learn about this when you start learning about the steel structure design. So connections are one of the most important aspects of the steel structure design. So you will learn that there are many types of connection which you can offer to the structure. And here you can see that it's not 100% fixed joint. It is partially fixed joint, because the bottom part, the bottom of this I section is free to rotate about the axis. So here you can see that unless you provide some additional connection support in terms of angles, you can expect some deformation of this beam, and some rotation is expected. So if you want to ensure 100% fixity in steel structures, you should ensure the support of the beam in all directions, right? So that is how I just intentionally selected these pictures to show you that how the degree of fixity may vary in the structure. So not all the joints which look like as a fixed joint get qualified as a 100% rigid connection. The best example of 100% rigid connection you can achieve in the material which is popularly known as reinforced cement concrete. I'll tell you why and how you can do it. Right. So with this, we'll go ahead, and we have sufficiently discussed that there are possibilities of partial movement in the fixed support also. Right. It may not be offering 100% resistance. Now this is a popular look of the RCC, typical RCC beam connections. You can see that there is a floor beam which are casted, and you may have a question that why they have not casted it completely, because here the slab will be coming and the entire slab will be casted together as a common slab all over the area, right? That's why they have not casted this particular portion, right? However, let's leave it aside. Our main interest is, you can see this connection. Just focus on this connection. This is typically repeated at every joint. You can see here every joint, right? It is similar. So what happens is, the reinforcement is first of all arranged, then the insertion of one beam within the another beam is done, right, by slipping in the reinforcing bars and properly tying them up. So what you are doing, you are interweaving the steel basically. And for RCC, the fixity depends on how nicely you are fixing your steel bars with each other. So keep it simple, like in case of RCC, and when you provide sufficient anchorage and connection of steel bars with each other at a joint, at a connection, whether it is a beam to beam, right now it is a beam to beam, or whether it is a beam to column, right? You have to anchor your reinforcing bars properly with the reinforcing bars of the column in case. And when you do it, you can develop 100% rigid connection. Why? Because the main reason is, or main benefit you can achieve it easily, is the casting process. If you focus on, or if you have experienced maybe earlier somewhere, uh, if you have seen the casting process of a concrete, you may have noticed that there is a practice of casting of concrete at a time for at least beams and slabs. So generally, beams and slabs are casted monolithically at a time along with each other. So what happens is, there is no possibility for any of the lagging of the fixity at the support. So here you can either at a support or a joint. So here you can see that this joint is highly interwoven by means of rebars. That is first thing. You can see there is a little difference in the height of this beam. This, let us say where the cursor is moving right now, this beam is, getting inserted in this main beam. And that is how now when I cast my slab, everything goes inside. So everything is now at a same level, right? When I introduce my slab over here on this entire opening, right? Otherwise, if it is a semi-open area, then even you can cast, or you are going to cast this particular top portion together. So when you are casting it together, you can develop tremendous fixed joint. So in nutshell, I would like to tell you that if somebody asks you that in which type of structure you can expect 100% fixity at the support or a joint, definitely your answer should be in RCC structures only. Right. Here I have selected this. Just notice the rebar connection providing rigid connection. You can see that these are the top bars. Just focus the movement of my cursor. This bar is, starting here and reaching over here, and it is, bent over there on the main reinforcement of this another beam. And it is also rigidly tightened and connected by means of wires with the reinforcing bars of this column also. So now you can expect, you can see here there is a upliftment, there is a bending of this bar. Bottom bar also are bent upwards, and the top bars are bent downwards. So when you develop this kind of arrangement and tighten them with the other reinforcing bars, you can expect 110% fixity. Right. So now you can expect that whenever we are going to cast this entire joint, it is going to offer you ensured fixity of all these beams connected. So indirectly we can end up with having this beam as a fixed beam, which is connecting this column with another column. Right. So in future they will be casting this, and you will see that they have developed a fixed joint at this particular junction. So naturally, this beam is also going to get connected with the opposite column in a similar way, and that is how we can ensure ourselves about the fixed connection. So I just wanted to show you, because there is no point of directly starting the numerical without the actual understanding of how basically the fix and looks like, how you can develop in variety of the materials. It will enhance your understanding about the fixed beam. That's it. So the only intention behind offering these pictures to you was, I just wanted to share that how the fixity varies with the material or with the construction techniques. Sometimes rigid connections are welcome, sometimes they are getting avoided. So when they are getting avoided, that also I'll let you know once we are done with the some of the numerical examples and practice on the analysis of fixed beams. So here we are not addressing to analyze or trying to analyze the system of the fixed beam or frame. We are just analyzing a single beam, right, which is fixed at both ends. So now when I say fixed, that means you should know what we want to analyze. This kind of, you can visualize any of the pictures which just now we have gone through, right? Any of the pictures. So you can visualize the fixity by these pictures. So what are the spatial features of the you know fixed beam? So what makes the beam fixed? Let's go through that. I hope you are clear on visualization of the fixed beam. Right. Okay. So the rigid connection of beam with the support makes the beam fixed. So that is the primary criteria. So the connection of beam with the support, or maybe the another member, which makes the beam fixed. So the key word is rigid connection. Okay, you must have a rigid connection, and I hope you know what is the meaning of the rigid connection. So As usual, can I have an open answer? This is a question to the everyone. Who will tell me what is the rigid connection? Raise your hands, please, so that we can do a two-way communication also. Very quickly. Rigid connection, very simple. Ala Hamza. Okay. Yes, Ala.
Yes, sir. It's provide reaction for three elements like for fx and fy and the moment.
Okay, great. So that's a very
It's rigid.
straightforward and yes, simple answer. So that's correct. Thank you. So that means a rigid connection can offer you variety of the reactions, including displacement, reaction to the displacements, and reaction to the rotation. Right. So it doesn't allow your beam to move in any of the direction. So that's why it is called fixed beam. A fixed beam cannot displace in any of the direction, as you know, right? All the three types of the reactions are offered by a rigid connection. So the forces include induced at the fixed end are bending moment, vertical reaction, and the horizontal reactions. And if applicable, torsional moments are also generated. If you apply torsion on the beam, torsional reaction is also offered by the fixed support because it is rigid, completely zero movement, right? So whatever nature of it's immaterial that whatever type of the action you are employing on the beam, it will definitely get resisted by the fixed beam if it is a fixed support. So whether you create or induce torsion, whether you create bending, or you create shear force, displacement, whatever, lateral movement also, nothing will be possible. So everything is so rigidly bent for this particular beam, which makes the structure rigid 100%. Right? A fixed beam can offer better resistance to the bending and shear deformation due to the effective transfer of the forces at the ends. So here we are appraising the fixed beam for its capacity to resist the moments and deformations and other transitions effectively. Right. So definitely it's a powerful tool to transfer heavy loads of the structures. And that is why all the skyscrapers, all the tall buildings, all the important RCC structures, I mean structures are created by RCC primarily. Because RCC is the one of the most desirable material which offers you 100% fixity, as you know now. And why it's also known to you. Right? Unlike the simply supported beam, where bending moment cannot be transferred to the end supports, and therefore large bending deformation is expected in simply supported beam. Now if you compare or visualize, let's visualize these two things together. On one end, on a left hand side you have a fixed beam, on a right hand side you have a simply supported beam. Now in simply supported beam you don't have reaction to the bending, so whatever action which is generated in the beam due to bending remains within the beam itself. It doesn't go anywhere. So when it doesn't go anywhere, the beam, it's a responsibility of the beam itself. Because see, when you don't have support, you have to hold the weight, right? But if you have some handle, if you have some carry bag, you can put everything together inside. But the poor chap who is simply supported beam doesn't have anything to transfer from one end to another end because it's having simply supported supports. So the simple supports cannot offer you the reaction to the bending, and that's why the complete bending deformation will remain within the beam itself, and that is why the beam, in case of simply supported beam, will always suffer from the large deformation due to bending. And you will notice that the dimension of simply supported beams will be always larger than the fixed beams. This is the basic reason why it happens so. So I hope you understand now slowly the basic behavior of the beams and how the support conditions influences the bending behavior of the beam. If you have a fixed beam, less bending moment will be developed. I mean, better bending moment will be resisted, and that is how the beam has a chance to transfer the bending from one point to another point, or from one element to the another element, so that you can reduce the requirement of the large dimensions of the beam section to the smaller dimension. And that is why popularly rigid structures are very popular in the multi-story buildings, where the dimension of the members really counts a lot, right? So that's that. So this is the special, I mean, these are the special features about the fixed beam. So now what's next is the behavior itself, right? So let's check them out. So I'm going to explain the basic behavior of a fixed beam under the vertical forces. So imagine that this is a beam having two ends fixed. Let's say left hand side is beam point A, right hand support is support B. So we have two supports. We have L is the length and centrally loaded as a point load. Right. So now because of the action F, let's see what are the reactions induced. So naturally, there are two vertical reactions which will be primarily developed called VA and VB. You can very well imagine that any fixed beam or any fixed support will be first of all offering you vertical reaction. Then there is a second set of the force reaction that is offered by the fixed end is horizontal thrust. Now, sometimes due to the limitation of the force type, uh, because of the absence of the horizontal thrust, horizontal reactions now are not always possible. See, because when you don't have action in horizontal direction, you don't expect any reaction in the horizontal direction. It is as simple as that. However, ideally, we are discussing the ideal end moments or end forces in the fixed beam. So here you can see that HA and HB are the horizontal reactions developed at the fixed support. Finally, the king of the ring moment comes into the picture. This is the reactive moment. This moment is known as fixed end moment. I repeat, please remember this because it's a very important quantity for us. Sometimes horizontal forces may exist, may not exist, it doesn't matter, right? But these two are the bare minimum forces always you will notice getting developed at every fixed support. And out of that, this is the most important one, that is called fixed end moment, right? And it is always in reactive in nature. You can see that it is anti-clockwise. So if you cut a section near to the support, due to the force there will be a clockwise moment, and in the beam the moment nature will be clockwise, but at the fixed end the nature of the moment will be anti-clockwise always, right? So that is that, and these are the quantities which are developed at both ends. Right. Because of that, we have MA and MB. The another popular legend or the symbol for this moments is FEM, fixed end moment. FEMA, FEMB, or you can use FEMAB and FEMBA, which is the joint comes first as a suffix, right? So end A will be FEMAB, and from point of B it will be FEMBA. That's it. So whatever symbol you want to use, you can definitely use it. Fixed beam moment, fixed end moments at A and fixed end moment at B, right? Uh, I noticed somebody raised the hand. Anyways, if you have question, you can put it them in the chat box. Definitely, right? Don't worry. I'll get back to you. Okay. So these are the primary forces, or we can say end forces, or we can say reactive forces, which are developed in the fixed beam in a simple form of the forces. Now, if you change the nature of force, this reaction doesn't change. That means the nature of reaction doesn't change. For example, instead of point load, if I convert this point load into the UDL entirely spreaded on this complete length L, the end reactions in nature or nature wise it will remain same. That means two reactions and one moment. If you change UDL to the varying UDL starting from 0 at point A and reaching maximum at point B, so it will be a triangle loading. Again, the nature of the forces induced at the support will remain as it is. So two moments, two vertical forces and two horizontal forces are developed at both ends. So it practically it has no impact or no influence of the loading on the nature of the forces induced at the fixed end. So always you will have the minimum these three sets of forces. If you are dealing with the space structure, you will have one vertical reactions, two horizontal reactions, and three moments around all three axes. So basically you have six reactions, right, at each end. But the nature will not be changing if you change the load in a particular fixed beam. Right? This is just for your reference. Don't think much about it because we are going to deal with point loads and UDL on the fixed beam only. However, their positions and compositions will be changing for a complexity of the numerical. But primarily, we are going to see that now the next task is if I want to calculate these values, reaction values, how should I proceed? Because in case of simply supported beam, within a no time you can quickly calculate the value, numerical value of VA and VB. For 1 minute you assume that this beam is a simply supported beam. There is needless to ask you a question that what would be the value of VA and VB. It will be definitely F by 2, that's all. You all know that because it is a centrally loaded point load, right? But in case of fixed beam, can we directly calculate this vertical forces, this moments, even in case of this horizontal forces quickly? The answer is practically no, because it is not statically determinate structure. So what's the solution then? What to do? Right. So for that, we'll take help of two old concepts. One is method of superposition, and second is moment area method. Right. So in moment area method, you remember that we used to develop the bending moment diagrams of the beams according to the given loading condition. If you recall, we have developed the diagrams like triangles, like parabolas, like combination of both of them, like cubic parabola and so on and so forth. So now we know that what are the area, how to calculate the area of these bending moment diagrams, right? So this concept we are going to utilize once again. And in parallel, as I said earlier, we are going to use the concept of superposition. That means first you segregate the structure and then you rejoin the structure. After segregating, you can analyze the structure as simply supported and then you can rejoin them together. How to do that, I'm going to explain in the next slide. But before that, you just see that this is the deformation of the beam. So the fixed beam combines two types of bending, nature of bending, right? This is sagging moment, which takes place in the center part of the beam under the force, and these two are the negative moments, which are developed at near about the support. So this is the speciality, this is a spatial behavior of fixed beam, that in a fixed beam you have a combination of bending itself, sagging as well as hogging. So hogging takes place near about the support and sagging takes place within the span. Right? The approximate length of this negative moment remains as L by 6 to L by 4. That, however, depends on the nature of the loading and other factors. So don't worry about the length of these negative moments. But we know that at least now in fixed beam, we have two types of moments. One is negative moment, that is called the reactive moment, support moment, end moments, and second is the positive moment, which is known as span moment. So always remember, in a given fixed beam, irrespective to the type of the loading, two types of moments are expected. One is positive moment, second is negative moment. Positive moment is a span moment, it's a sagging moment, and negative moment is known as end moment, or it's a hogging moment, right? I hope I'm clear, and I'm also not rushing hard, so that you can clearly understand what, as I speak, you should grasp these words in your minds, right, directly. Okay, so with this, let's go ahead and let's see how further we can analyze this particular beam for our basic purpose. Now, what is our target first? Our first target is to calculate the value of moments. I want to know the numerical value of MA and MB. Now, how do I get it? And then once I have this values, I can definitely work out the values of VA and VB. Now, there is a concept of compatibility, right? Which you probably have come across. I'm not sure, but basically it deals with the structural integrity of the connections. So, in short, according to the concept of the compatibility equation, the net movement should be zero in the fixed beam at the supports, right? Now we all know that there is no chance for any movement at the fixed end of the fixed beam, right? So we'll be utilizing this concept, and how to utilize that we are going to see. This is what is the text which deals with the same thing which just now I have explained. That at supports you have hogging moment, at span you have positive moment. Okay, now what are the steps for the analysis? Obtain the simply supported beam with loading from the given fixed beam. That is a very important and first step. Obtain the simply supported beam with loading from the given fixed beam. So that means you remove the fixity, right? That is the first step. That is your ideal step. So when you remove the fixity, what remains is the simply support. Remove the fixity, that means you are not considering end moments at this moment. So when you avoid end moments, it becomes your simply supported beam. So convert fixed beam into the simply supported beam. That is the first step. After doing it, draw the bending moment diagram of simply supported loaded beam. You have removed the end moments and you have converted the fixed beam into the simply supported beam. So now it is easier for you to draw the bending moment diagram according to the new structure that you have assumed, right? Now what next is, draw the bending moment diagram for the beam with only the end moments. Please remember, what we are doing, we are using the method of superposition, and we are segregating the beam in two parts. In first part, you have removed the end moments and assumed that the beam is simply supported, and you have developed the beam diagram. But the removed one, that is called the fixed end moments, are now applied only without any external loading. Now we are not using external loading, we are just applying unit values of end moments. And based on that, you can still draw the beam diagram. So once you have developed two bending moment diagrams, first bending moment diagram is due to the loading, and second diagram is due to the end moments only, which you have removed earlier. And in third step, you have to combine both these diagrams. So combine the bending moment diagrams for net bending moment diagram of the original fixed beam. And then you can locate the point of contraflexion, where the sagging moment becomes hogging, and hogging again becomes sagging. So you know the definition of contraflexion, point of contraflexion. It is the point where bending moment changes its numerical sign from positive to negative, or from negative to positive. That's it. So let me show you how to do it. Sorry. Uh, that's a fixed beam with a point load. So first of all, I have removed the end moments. So it becomes my simply supported beam like this. And plus, now you can see that I have only applied the end moments on this beam. Okay. So when you now club them together, it becomes ultimately your figure number one. This is the figure number one. This is figure number two, and this is figure number three, for example. So if I club them together, I can achieve my original structure. So you can see that what I have done, I have segregated vertical reaction and moment. So I have separated them. So now for me, the life has become very simple. I can analyze this happily for the bending moment diagram. Yes, you know that it's going to be a triangle, right? And here in this case, again my life is very simple so that I can apply the unit weight of the moment. So for me, the diagram for this structure will be nothing as more than a rectangle, because at both ends I have equal moments, right? So my diagram will be nothing but more than a rectangle over here, as you know from the earlier concepts. Right? So now always remember that when you apply only moments, do not use any loading from the span in the original structure. Here you can see once you have already considered the original load, so there is no need to reuse it over here. Only use once in the first structure itself and develop your BM diagram, and then only apply bending moments which you have released, right? So always the diagram of the release structure because of moment will be always a rectangle. That you have to remember, right? It will be nothing more than a rectangle. The only thing is it changes when you have continuous beams, because on one end you have fixed beam, a fixed end moment with x value, but in the next level, if you have another beam which is available over here, and if it's having different span, then definitely the fixed end moment will be different. But that is a complex or next level example, so don't worry about it. Just now for a sake of understanding, you can uh, understand it that when you want to offer the fixed end moments, it is just a rectangle, that's all, right? So now I have separated both the structures. Now let's see what's next is, see, now here the complete moment is a sagging moment, so my bending moment diagram will be positive, right? So I'll be drawing it below the line, as you know, right? For the sagging moment, bending moment diagram is developed below the line. So the value maximum ordinate, you know from the earlier analysis, is WL by 4. This is a standard formula. So C is nothing but the pointing at the location of the force. So you have this diagram with you, and in this case, this is, let us say, diagram A. This will be diagram B. The red line is just a beam, the rectangle is this, right? So the value of this moment is nothing but a unit value. It may be MA, it may be MB, both are same, right? With the same amount of the moments at each end, right? Constant moment, we can say constant moment. Okay. Now, let's combine them together. So here we have combined them, and this is the net bending moment diagram. When I'll be drawing the net bending moment diagram, this upper portion will be getting cancelled. So we have two orange triangles and only one, this much amount of the yellow triangle will be remaining. So that will become the original combined diagram for this structure. Some books refer to produce this diagram above the line, so that is completely fine, don't get confused. In that case, the only thing is this triangle will be projected upper side of this line, so it will be starting from here and it will be going like this. So right now we are stick to our old concepts. Once we have done a concept in our mind, it should not be changing. So that's why always we will see that our sagging moment diagram will be below the line and hogging moment diagram will be the above line. Right? So this is a combined BM diagram. Right? This is also a kind of shear force diagram which is based on this simple supported structure. Right? So There is no shear force as such on this beam, so there is no point of drawing the shear force diagram. So always, for even the fixed beam, the shear force diagram is as per the simply supported notion only. The only change in the diagram is the bending moment diagram. Right. So now this is the concept, but we need numerical values also. So now our actual step starts. See, we have already performed this segregation. We have done the analysis by and large. This is your point load. This is your moment. So because of that, we have all the important ordinate values. Here, the value of BM diagram due to the point load is WL by 4, where L is to be assumed as the complete length of this beam, right? And W is the load here. Right? So this is a W load and L is the length. It's my error that I could not show that dimensions over here. I should have, could have put over here. So in future I'll take it. So here WL by 4 and M is the value of moment, unit moment at both ends. Right? So now let's see. We know the relation. We need to combine both the areas. Area of diagram A and area of diagram B should be 0, right? So that summation should satisfy the requirement of the compatibility condition. So when you club them together, nothing should be in the remaining part. So when you club them together, it gives you 100% compatibility. Right? So that is how we can basically add both the diagrams together like this. The areas you have to add, please remember the area, not the values. The area of diagram 1 and diagram 2 you have to club together. So 1 half BH, uh, where H is nothing but the value of the moment and B is nothing but the L, right? As you know popularly. And this is the area of this diagram, rectangle. L is the length and M is the value. So ultimately we are interested to find out M value. So it's now very simple. 1 half BH, H is WL by 4 and L is the length. M into L is already with us. So which gives you a value of sorry, value of M equals to WL by 8, and that is negative, right? When you change this value from this side to that side, it becomes negative. So the value of friction moment on one end is always negative and the value of the other friction moment is always positive. Now that depends on which you call positive and negative. That's completely up to you. So here in this case, on one end, you can say that this is the anti-clockwise moment. So we'll call this positive, and this is clockwise moment. So we'll call it negative. Right. So the value doesn't change, only the change in the numerical sign that you have to take care. You will see in any standard reference, you can go to the internet sources also, you will find the same thing, that in a fixed beam the moment values are same at both ends, provided that the loading is symmetrical, but the numerical signs will be different. One will be clockwise, second will be anti-clockwise. So here you can see that in our case it is anti-clockwise, so we'll consider this as positive moment and this will be the negative moment. But you have at least learned how to obtain that. Right? This is a simple form, this is a simple step. You have to calculate the bending moment diagram, draw that diagram, obtain the value of this area of the BM diagram, obtain the value of area of friction moment, and club them together and find out the value of moment. Once your moments are calculated, the rest is very simple. You can calculate the vertical reaction at both ends by means of simply supported beam concept. So it is just as good as shear force at both ends in case of earlier calculations. Like you can simply say this is, if it is W, then the shear force will be W by 2, W by 2, right? So hence all the reactions are calculated. So within a no time, you can pursue or you can understand that definitely it is possible to calculate friction moments as well as vertical reaction for fixed beams. So now you know we have learned how to calculate friction moments as well as vertical reactions for fixed beam. with a simple understanding, with a simple example. And I'm sure that there is nothing tough to understand on this. But this is one of the techniques, and this becomes little complex when you have complexity in loading, right? So we'll take some similar examples, numerical examples also will take up, and it will enhance your understanding how to calculate unknown quantities at the supports in the fixed beam for variety of the loading in future. So in the next class, after having some rebrushing of the old knowledge, as we decided, we will carry on with the calculation of the other quantities. So I think I've taken your much time, more than 4 or 5 minutes. So I'll be quickly going through this. Now you can see here MA, MB and V and VB are written over here. These are the values that you can expect, right? So the content for the next session is analysis of fixed beam with different load types. So what is the takeaway of today's session? That means, what is a summary? A fixed beam can be analyzed by employing the principle of superposition and moment area method. The beam is separated by means of end moments and reactions as if the simply supported beam with the given load. Right? This method is convenient for symmetrical loading on the fixed beam only. Right? So likewise, you can see that we have come up with the first step, baby step, towards analyzing the fixed beam in the given standard loading case. Okay, so I'll end up the session over here, and I appreciate your involvement. Thank you very much for joining today's session. In the next session, we'll do some more interesting work. Right? So carry on with your learning. Thanks for joining.